Alright, so hello everyone. I just wanted to make these videos in addition to the in-person tutorials I'm holding because I understand that with the teaching method chosen, it can be quite challenging for some students as it's designed to improve critical thinking and collaboration. I also realize that I'm rapping, that just kind of happens with me, so I'll just try to slow down, hold on. Okay. The goal of the in-person tutorial is not for me to give you guys all the answers, but to guide you to it. However, these videos will serve to be more akin to the traditional style of teaching seen in lectures, provide standard definitions, minor theory, and explanations for the content. You'll be given detailed answers for these videos, and you can ask questions in the comment section for any of them if you have any. Right, like I understand that I might be stumbling through this, but I've tried to be pretty detailed. Okay. So with question one, I saw that this got quite a few people, as I see people lacked this definition right here. This is something that is explored in mathematical reasoning and usually briefly in other introductory math classes dealing with sets. But in case you weren't shown this or just simply forgot, I provide the definition here, and this is all we're pretty much going to use to answer this question. Very similar to set theory products, Cartesian products, but yeah, we're just going to use this definition here. So it's supposed that V and W are finite dimensional vector spaces over a field F, which could be like R, C, whatever you want. Here, specifically, it's R. Then the direct product of V and W is the set V times W equals VW, and you'll see that the order is listed from the first one's listed here, then the second one's listed here, with some vector V element of the vector space V and some vector W element of the vector space W. Alright, so this is pretty much what we're going to use, because if we look up here, we see that R3 is listed first, so it'll be first here. Additionally, P1 will be listed second, as it is second in the order of Cartesian products. But yeah, in case you're not aware of what Rn is, I provided another definition right here. So suppose V, some vector V is an element of Rn. That means that we're going to get out of the form of a column space here, which is basically n rows and one column, or you can list it like this, just as brackets with V1, V2, up to Vn, because it has n pieces, right? N dimensions. And these are going to be elements of the column space Rn, where the size is, once again here, row times column, just equal to n times 1. I've also listed the definition for what a polynomial Pn is for some field F. Right, and here we're going to have it as some coefficients a0, a1, a2, an with respect to some degree coefficient x. I also got questions about do like the letters themselves matter? And they do not. The only thing that really matters is how you define the letters themselves. Right, so if you want to use B here instead, you can use B. I just chose A because that's pretty traditional, standard. And we define it by a degree less than or equal to n, right? So now we're going to use these pieces to figure it out. So from this definition here, we see that V times W is equal to VW, listed in this order, so we're going to use this here. So we have our space R3 times P1, that means it's going to be R3 then P1, equals, does it equal this? That's listed up here, so we're going to check that. First, is ABC an element of R3? And we see that, yes, it has 3 pieces, 1, 2, 3. So it is an element of R3 in a column space, and it's listed one-dimensionally too, right? Only one row. All right, then the second piece is our polynomial. So is D plus EX P1, because that's what we want up here. And it is because we see it's of degree less than or equal to 1. So these are correct. Then we check the order. It's first, second. This is correct, so therefore this is all true. All right, I'll move on to the next one. All right, this one, another one. A lot of people weren't sure what to do here. Some people tried to prove that the addition property held and the scalar property held for multiplication. You didn't have to do that. You're supposed to take the traditional definition of what it means to add and multiply in a vector space to show that either one of the vectors, at least one of the vector space properties failed, therefore this is not a vector space, or that all of them held, so it's true. And the one here that we're specifically looking for is that, quote, there is a 0 element that has 0 plus v equal v for all v that are vectors within this supposed vector space. Right, so we can check, we can sub in 0, So let a and b equal 0, as these are our pieces that we can sub into 0 for. We do not do that with x. then a plus bracket 1 plus ax plus bx squared equals, then we put zeros in for there, we find that equals x, which does not equal 0. Therefore, by this property defined up here, this is not true at all. So therefore, 0 is not an element of S, thus this is not a vector space under the usual addition and scalar multiplication. And I just have a tip here for you guys. The 0 element is often the easiest / quickest to check for linear operations, vector spaces, and subspaces. So it's the easiest one to just be like, just put in 0. Does that work? If it doesn't work, good. That's it. You only need to show one. Okay. What's the next one? The set M of all polynomials of the form at squared, where a is an element of R, is a subspace of P. So I got some questions too about what is at squared here? Like, why does it look like this? Basically, you can just imagine it as a subspace of the polynomials, right? Because this would be this could be like P2, this could be P3, right? Such that we have the coefficients with the constant and the first degree are 0, and we have some at squared. So anything that is greater than or equal to this could be considered like to include this. All right, so how do we show this as a subspace? So we're first going to check that 0 is an element of our set M. Then we're going to check that for all vectors v and u that are elements of M. If we add these together, is it also an element of M? Which is checking closure under addition. So if we add a vector within the set and then another one, will it still be within the set itself? And for all vectors v element of M and scalar multiples c element of R, you can choose any letters once again. I just chose C because I like C. Is c times v still an element of M? So does it close under multiplication? If I multiply the vector by something that's a scalar, will it still be in the set? All right, so to check for 1, we're going to sub in our 0 here. And we see that we have our A as an element of R as a subspace. So we're going to deal with A. So we're going to let A equal 0. Then we're going to check if this is equal to 0. Then at squared equals 0t squared equals 0, because 0 times anything is just 0 here. So therefore, 0 is an element of M. Now we're going to check for addition. And how you start the proof for addition is you're going to suppose two vectors, right? Because we're going to use the definition here, v and u. So we're going to let at squared, bt squared element of M, because these are of the form this. Then at squared plus bt squared equals a plus bt squared. You just factor out the common t squared, and then basically what you want to do is you want to check is if I add a plus b, is that still within our space here, which is a is an element of R. So we say that since a is an element of R and b is an element of R, a plus b is going to be an element of R, right? That's just the property there. And so this is just going to be an element of M as well, as defined here. Okay. Similarly for multiplication, we're going to use the definition here. We see that for all vectors v element M and scalars c element R, c v is an element of R. So we're going to suppose some vector is an element of our set. So at squared is an element of M, so it follows this. And c is an element of R because we're dealing with our R right here. Then c at squared equals bracket CA. I just wanted to show that explicitly, just to show that we're going to try to be proving that CV is holding. So since A is an element of R and C is an element of R, CA will also be an element of R. That's just another property of multiplication. Therefore, this will be an element of M. And so since all three hold, M is a subspace of P. There we go. All right, next one. This one. Okay. I did get someone who wasn't quite sure what X element of Rn meant. So I just wanted to try to visualize it here. So once again, we're gonna show what Rn is here. I brought this back from question 1. Rn is just a column space of n dimensions dealing with n pieces, with the size row times column equals n times 1. And if you wanted to visualize what that looks like, we have Ax equals 0 implies we have m rows for our m times n matrix here. And we're going to multiply that by x, which we've defined to be an element of Rn. So it has, hold on, let me just fix that. Let me fix one thing, guys. Let me just say 1n. There you go. This is why I speak things through, because I figured them out. But yeah, so one column n rows equals 0. and then we show that x less than n or x greater than n, this will fail to multiply through the dimensions because we want these pieces right here. So this is a quick way to just check if it's even of the correct form to deal with the question in the first place. If this isn't true, then it's just gonna fail. It's not possible. So you can check that. But now once again, we go back to what are the subspace. So is 0 an element of n? Well, let's let x equal 0. Then we just have a times 0, which, well, that's just 0. So yes, it's an element of n. Then we want to suppose two vectors within our element of n, such that we can add them and see if it's still an element of n. So then we deal with a bracket x naught plus x1, because we're dealing with x here. Some people were like, maybe I do a naught and then a1. No, you do x1, x naught, x1 right here, this piece. Just get rid of that. Okay. Then a times x naught plus x1 equals ax naught plus ax1, right? Because we're using the distributive property, we can do this. Just goes into there. Since x naught and x1 are an element of n, that implies that x naught and x1 equals 0, because this piece needs to be hold true. Right, so that implies that ax naught plus ax1 equals a times 0 plus a times 0, which equals 0 plus 0 equals 0. So therefore x naught plus x1 is an element of n, so it's closed under addition. Then we're going to let x naught be an element of n and k an element of our field R here. Well, you can pick any field that you want, really. It's not really explicitly defined, so it can be like f. Then a k x naught equals k a x naught. Once again, we just go back to our definition. Since x naught is an element of n, x naught has to be equal to 0 by this, which implies that k ax naught is equal to k a times 0, which is equal to k times 0, which is equal to 0. So once again, we get kx naught as an element of n. So all three hold, so it is a subspace of Rn. Glad I caught this thing right here, because I wasn't paying attention. Okay. So this question. I didn't answer this for one group in particular. We were only really looking for the 0 vector. That's what we were looking for, but one group did an alternative answer. So I didn't really reply very clear there, but I will accept alternative answers, absolutely. Like, you only need to show one of these don't hold. So for the group that did the other one but didn't do this one, yeah, you guys still got it, right? Like, don't worry about it. It's just being silly. All right. So this is a Q of all matrices of form this, where is an element of field, is a subspace of M22F. So first we can just check the form. Is the form right? Well, we have 2 rows, 2 columns, so the form is correct. Then do we have 0 an element of Q? Because we want our set Q. So we're going to let A, B, D equal 0, because those are things we can control by this piece. Then A, B, 1, D is equal to this, which is not equal to 0, so it is not an element of Q. So that fails. So this is a solution we wanted. One group in particular that did other ones, and that's great. Moving forward, I will not respond like that ever again. Anyways, so let VU element Q, then V plus U equals blah, blah, blah. We just define it to be some arbitrary matrix, A1, B1, D1, A2, B2, D2. So we combine these together by the addition property. Then we want to check one thing. We want to check that since all of these have been defined to be an element of F, would adding them still be an element of F? And we find that is true. The only thing that fails is this piece in particular, right? However, 2 does not equal 1, as we see here. So adding them together is not an element of Q, which is our set, so that also fails. Similarly, multiplying will fail because, even though all the other ones will be right, because multiplying A1, B1, D1, and C, where they're all elements of F, those will also be in the field. Multiplying 1 by anything that isn't 1 will fail because we need to have 1 up here. As I said here, however, if C does not equal 1, C times 1 does not equal 1, and so it will not be an element of Q. So since at least one of them failed, Q is not a subspace of M22F. So yeah. All right, 6, I think. Oh, 6 is just more of a definition, which people also lacked apparently. So given T is a linear transformation, that's an important piece. with tx equals ax for r to the n. This is also important because we want the size of a, which is with respect to the transformation here. For our n, we take the size of a to be row times columns, which is going to be equal to dim v times dim w, where we define w to be rm and v equal to r2m. Right, so that's going to imply that the size is going to be 2m times m, which is not equal to m times 2n up here. So that's just wrong. Right, and that's just more of a definition. So if you lack that, well, you just got that right there. Here we use a similar definition as we did with in 6. Like we can just find the dimension similarly as defined here. Well, it's quite literally defined. Right, so given t is a linear transformation with tx equals ax for rn, we have that we're going from v to w. So the dim of w we see is the rows, and the dim of v, which is R3 of our column space, is equal to the number of columns, right? 3 columns, 2 rows. Anyways, so to check if it's a linear transformation from v to w, we're just going to check this really quick, and I just show that the dimensions match right here. Right, 2 times 3. We're going to do the following properties. We're going to check addition and then scalar multiplication. So for addition to hold, we need to have 2 vectors u and v. We're going to add them within the transformation, and then we're going to apply them outside of the transformation. We're going to see if those hold. If it doesn't, then it's not a linear transformation, right? So tu plus v equals tu plus tv for all vectors v, u element of our vector. Some vector space that we've decided. And then tkv equals ktv for all vectors v element v and scalars k element f, where we have just some sum field, which isn't really defined here, so we can just suppose this. So to check this using tv equals av, we're just going to get rid of the t, we're going to apply our transformation, which goes to a. So t will go to a. So tu plus v equals au plus v, because t goes to a. I'm going to distribute that in, which is equal to AV plus AU, well, AU plus AV, sometimes I do the other way around, which is equal to TU plus TV, and therefore property 1 holds, right? TU plus V equals TU plus TV. The second one is TKV equals AKV. Once again, we're just putting A where the T is, which is equal to KAV, and by our linear transformation definition, we can sub back in T for A, as we did up here as well, to get that TKV equals KTV, so that property holds. And we say since both properties hold, TV is a linear transformation from V to W, and so this is true. And I have another tip. If you can quickly just show that T0 is not equal to 0, then it will not be a linear transformation. Showing these two above actually gives us a lot of properties without even having to show them. So if these two are true, we automatically get that T0 will be equal to 0. So this is a really quick example of how to counter the assumption that it's a linear transformation. Just show that T0 is not equal to 0. Here we have another one. So let p goes to p be given by tpx equals px squared. So we're going to square within the functions themselves. Right, so up here. Then t is a linear operator of p, where p is the vector space of all polynomials over c. Once again, we're going to use our previous definitions of tu plus v equals tu plus tv for all vectors v u element p here, because we have our set here. We look at the first one, and tkv equals ktv for all vectors v element p, once again up here, as I've circled pink and blue with respect to what their importance are, and scalars k element c because we're over c. So now we let px, qx be an element of p up here. Then tpx plus qx is equal to, we're going to apply the transformation. And as we see with the transformation, it is just squaring the inside of the functions themselves, not the outside. So we take px, we square the inside, take qx, square the inside, and we end up with px squared plus qx squared, which we can just reverse the transformation property again. So if this holds true, we can go the other way around to get that tpx is equal to px squared plus tqx is equal to qx squared. Right, so we see that that holds, this property right here, number 1. Second one, we're going to check scalar multiplication. So let px be an element of p and q be an element of c. Then t kpx is equal to kpx squared, because we do not apply the square to the constants within the transformation. We only apply them to the function, as seen up here. Which then we're going to reverse the transformation again. So if tpx is equal to px squared, then we're going to go from px squared is equal to tpx, right? So you can go both ways. And we get that's ktpx, which holds. So once again, since both properties hold, t is a linear transformation from p to p over c, so that's true. And I actually showed this more generally here. If we have tpx is equal to pxn, so like any x to the n within the function itself, where n is an element of the natural numbers, this will work, right? So this is a useful generalization. So if you ever get like px3, px4, px5, px1, all of these will work. Just a bit more generalized right there. Similar to 8, except we're squaring the outside this time. And one thing I'll say is, as I've actually noted down here, is squaring when there's addition involved usually doesn't go well. So yeah, let px qx. Once again, we're going to define two functions with respect to our polynomial space. We're going to try to add them together, but what we're going to end up with is we're going to end up with the inside being squared, which is going to give us by the square, well, px squared plus 2px qx plus qx squared, right? You know, a plus b squared. However, this is not equal to tpx plus tqx, right? Because we have this extra piece in here. So we can just find a counterexample to prove that this doesn't work for all vectors. One would be px equals x and qx equals 1, right? Because we're gonna get x plus 1 squared does not equal x squared plus 1. Right, so this is going to be our counterexample up here. Scalar multiplication does work though. Let px element p and k element c. Then tkpx equals kpx squared, because we're not, once again, squaring the scalar multiple here. We're just squaring the function itself. And then we're going to reverse apply this to get ktpx. So there you go. But since one of them failed, this is not a linear transformation from p to p over c, right? The additive property. And I generalize it down here. If tpx is equal to px to the n, where n is an element of the natural numbers minus the element 1, so here, this does not exist. This will not work. Where n is an element, well, the set n is equal to 1, 2, 3, dot, 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 n minus 1 to n minus the element 1. Because n equals 1 works because it's just, well, it's just basically the function itself. So this is another useful generalization. So if you get 3 here, if you get 4, if you get 5, those will all not work. Okay, and 10. Stumbling away my way along this. What is this? Let S be the vector space of sequences A equal to A naught, A1, A2, dot, 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 over F. Let T go S to S be given by TAN equals AN plus 1. So this is basically just a shift to the right. So if you have elements like this, right, you're just moving to the right by plus 1. Right, 2, 3, 4, 5. This is what this means in case people don't know. So once again, we're going to have two sequences here defined to be our vectors. So let A equal A naught, A1, A2, dot, 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 B equal B naught, B1, B2, element of S, because that's the set that we're dealing with. And this piece is a bit funny, so I'll just explain this. But then TA plus B is equal to TA. We're going to expand the A's, right? Because A is equal to this, our sequence. Then we're going to expand the B as well. And then what we're going to do is we're going to group them together like this. Right? And then to get rid of this, to get rid of the T, we're just going to add 1 here, as shown up here. This is our transformation. So we're going to A1 plus B1 plus A2 plus B2 plus da 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 da. Now, since these, we originally grouped them together, we're just going to go back again, because this is just the grouping phase. Grouping. I'm going to go back, we're going to split them back up to a1 plus a2 plus dot 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 plus b1 plus b2 plus dot 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 dot. And by the definition of how we've defined our linear transformation up here, right, it's going to be a n plus 1, so we're going to do n minus 1. As I noted over here, a plus 1, a plus 2 plus dot dot dot. If we go back to t, that's going to be a1 minus 1, a2 minus 1 plus dot dot dot, which will give us back to ta plus tb, so the additive property does hold. Yeah, maybe I'll make some like visuals for this after as well. Yeah, I think so. Hold on. Let a, this is a scalar multiple, let a equal to our sequence again, and some scalar multiple over the field f. Then t ca is equal to t, we just distribute our c along the sequence. Then what we do is we apply the transformation, so add 1 to all of our subscripts for our a coefficients. Then we're going to factor out our c's, and just do this, and then that's equal to c times ta, because once again we're just going to subtract 1 from all of our subscript a coefficients, which will give us back to ta. Yep, so since both linear transformation properties hold, t is a linear transformation from s to s over f. Yeah, I guess that's it. If you have any questions, I understand completely. You can just ask them in the comments. I'm a much more eloquent writer than I am speaker. So yeah, that'll be much better. But anyways, thanks for watching. I'm probably going to make more videos for the other tutorials as well. Maybe make some actual theory videos as well, not like just tutorials, but yeah. So thank you.